Welcome to this video of the Simulink model presentation of the Kugle robot, a ball balancing robot. In this video, I will walk through this Simulink model that contains the nonlinear model of the ballbot, a nonlinear sliding mode controller for balance control, and a shape accelerated path following model predictive controller that takes in a path reference and feeds the orientation and angular velocity references to the sliding mode controller. Starting with the model itself, we have here a nonlinear quaternion-based model of the ballbot that is based on several ordinary differential equations put into a MATLAB script, and this block itself takes in torque inputs and outputs the 12 different states, which can also be visualized with several plots, such as the position, the quaternion, converted Euler angles, etc. The 12 states includes a four-dimensional quaternion state vector and its derivative, together with the inertial frame x and y position and velocities. The output, being the true states, are fed into a sensor model that takes in this 12-dimensional state vector and converts it into the according encoder ticks from the three wheels, omni wheels, an accelerometer measurement similar to what the inertial measurement unit provides, a gyroscope measurement, and a LiDAR heading angle, which is assumed to be provided by the localization software running on the ROS compute system. And this is fed into the estimator block here to the left, which is a combination of several extended Kalman filters. The main one is the quaternion extended Kalman filter that takes in the accelerometer measurements, gyroscope measurements, LiDAR angle, and outputs a quaternion and quaternion derivative estimate. Furthermore, we have a velocity estimator that takes in the encoder ticks and also some information about orientation and acceleration to smooth out and generate a properly filtered velocity estimate. Finally, we use normal integration of the kinematics to generate a position estimate. This is a crude estimate, and this estimate is more used as an odometry estimate fed into the localization algorithm running on the ROS computer. The estimated state vector goes into the sliding mode controller, in this case taking in a quaternion reference and angular velocity reference and outputting a three-dimensional torque vector for controlling the plant. This one is just based on a MATLAB model and is nothing else, nothing more fancy than just regular sliding mode control with a continuous switching law. Note the two sample rates. This is because the balance controller runs at 200 Hertz, while the MPC itself only runs at 20 Hertz. The MPC block takes in the state vector and outputs these two references for the sliding mode controller, and it does so in a bit more advanced way. It's using the ACADO toolset for running this model predictive controller. So ACADO has been used to generate optimized C++ code that has been converted into a MEX file for MATLAB. And this MEX file is called within this MPC block that takes in a desired velocity, angular velocity, a trajectory, and also obstacles, in this case, all modeled as static. So the trajectory is constant and the obstacles are also constant. This block then takes in the state estimate and computes the angular velocity reference, which is then integrated in the body frame to generate a quaternion reference together with the angular velocity reference. So now if we start this, we would see a plot appearing, a plot that shows us the reference trajectory. Together with the state of the robot itself. So here we get two views. One view to the left is the overall trajectory. The black lines is the reference trajectory, and the black dots is the current trajectory points that are used to perform a polynomial reference path fitting. The red points are the MPC horizon, so basically the predictions of the model predictive controller, and the blue arrow that we see on the right is the current velocity direction, while the small green line that you see sometimes is the current inclination angle of the robot. The green points are the corresponding path points that the MPC is internally using for computing the path following cost. And these are adaptively moved along the reference trajectory or the fitted reference path to match with this path following formulated optimization problem. And we see how the MPC is capable of navigating around these obstacles. The obstacles themselves are also included inside the optimization problem. The MPC is currently capable of navigating, or the MPC problem is formulated such that up to 5 nearby obstacles can be considered. And the implementation is made in such a way that the nearest obstacles are automatically detected, found, and then fed into the MPC itself. So obviously the MPC is trying to reduce jerky motion by both punishing the angular velocity and angular velocity the angular velocity and angular acceleration, while simultaneously keeping a distance to the objects. And this is actually done to ensure that the problem stays feasible, first of all. Since we have introduced some slack variables, that will help against the feasibility bit, since we also want to ensure that small uncertainties will not cause the robot to drive into the obstacles. We want it to keep a safe distance to the obstacles itself. If we look at the velocity plots, we will also see how to the left we see the x and y velocity in the inertial frame and the general norm here on the bottom. And the velocity reference has been set to 1 meters per second. And we see how it's able to track that, but we also see how it deviates away from the reference at certain positions. And the places where it deviates is actually when there is a large curvature, where it's more feasible for the robot to slow down to achieve better tracking, but this is again a tuning question. So in this case, it has been tuned to achieve more accurate tracking of the path over accurate tracking of the velocity. Simultaneously, if we look at the Euler angles, the reference and the actual angles, this is to show the performance of the sliding mode balance controller. We can zoom in and see that the controller is tracking the angles fairly well. But we can also see how the angles, the angle references, are changing in some steps. Let's see if I can. So we do see some steps here, but that is more obvious when we look at the angular velocity reference, where we will also see a nice tracking tendency, but we do indeed see the steps of the lower rate MPC, in this case running at 20 Hertz, such that we see the reference changing at a 20 Hertz frequency, which creates these sort of first order tracking steps. But this is the overall performance is that you don't see, or you don't really see these steps, since the first integration to the angle happens, creating a smooth angle reference, and also since it's running at 20 Hertz, it's smoothed out fairly well. So the tracking performance is achieved and on the balance controller, and we are capable of following a reference trajectory while simultaneously avoiding nearby obstacles.